this. Okay, so we're in section 2.2. We're talking about inverses of matrices. So an inverse of a matrix, first of all, for a matrix to be invertible, it has to be a square matrix. Okay, and I like this little marker here. I think this worked rather nicely last time. Yeah. We're in section 2.2. Yeah, this is what I want to highlight right here. A matrix is invertible. A matrix A is invertible if there exists a matrix C such that C times A equals I and A times C equals I. And I is called the identity matrix. So the identity matrix, as you recall, is the square matrix that has ones along the diagonal and then zeros everywhere else. Okay, that's called an identity matrix. And when you have an inverse, we call it A to the, it's written as A to the negative first power, but A to the negative first power does not mean 1 divided by the matrix A. You cannot take a number and divide it by a matrix. That is, you can multiply matrices, you can add matrices, you can subtract matrices, but you can't like take a matrix and divide it by a matrix. Okay, so if you multiply the inverse, A inverse times A, you get the identity matrix. But if you take A times A inverse, you also get the identity matrix. So in general, matrix multiplication is not commutative. A times B is not equal to B times A. But the inverse times the inverse A, the A inverse times A does equal the identity, and A times A inverse also equals the identity. Okay, so that's a property of an inverse. Now, how do you find an inverse? How do you find an inverse? Well, there's a formula here if you want to find the inverse for a 2 by 2. Okay, so how many of you have seen this formula? If you have a 2 by 2 matrix A and you want to find the inverse, how many of you have maybe seen this sort of cookbook formula? Solomon's seen it, okay. Has anybody else seen that formula maybe in the past? All right, well, this is how you find an inverse for a 2 by 2 matrix. Looks familiar, okay. It should be familiar to some of you. The expression under the 1, A times D minus B times C, is called the determinant of A. So you have this A, B, C, D matrix. If you take the product of the one diagonal, A times D, thank you, Justina, she's seen it too, and subtract the product of the other diagonal, B times C, that's called the determinant of the 2 by 2 matrix A. Now, this is a nice formula, but it's only good for 2 by 2 matrices that have inverses. Okay, not every square matrix is going to have an inverse. But you might wonder, well, you know, and here in example 2, they show you how to apply the formula. Easy, right? Not too hard. You might wonder, well, how else can inverses be used? Well, if you have the system of equations given by AX equals B, then you can solve by the solution X will be X will equal A inverse times B. Okay, that's one way that we can utilize inverses. So I want to share the whiteboard for a moment and just write that. Okay, if you have A times X equals B, and A is a square matrix, n by n, what's the vector X going to have to be? What are the dimensions on X? hold on, let me do it again here. Hold on, maybe so now I'm not talking that I have a 2 by 2 matrix A. I'm talking that I have an n by n matrix A. So it could be a 3 by 3, it could be a 2 by 2, but it could be a 3 by 3, 4 by 4. So that means good. That means so thank you everybody. Good answers. Solomon, Binyam. Vector X has to be an n by 1. Okay. And of course, then the matrix B, what would the dimensions on that be? Well, all right, so seeing some interesting answers here. So we know that matrix multiplication is defined between the matrix A and the vector X. So then n by 1 would be the resulting product. It always helps me to circle the column number of the first matrix and the row number of the second. But now look, what we're going to do here is the following, okay? We're going to take A times X, and we're going to multiply it on the left by A inverse. Okay. And therefore, on the right side, since this is an equation, it's a matrix equation, but on the right side, I'm going to multiply the vector B by A inverse. You notice if it's multiplied on the left side, I have to multiply it by the left on the right side. So what does this do for us? All right, I'll show you what this does. That's right. What does this turn into? A inverse times A. What is A inverse times A? That's the identity matrix. What's the identity matrix times the vector X going to equal? It's going to equal X. So you get a solution. Yet another way to solve a system of equations. Yeah. I like it too, Binyam. Remember, the identity matrix, like if you have if you have I sub 2, which would be 1, 0, 0, 1. Okay, and you multiply that by, yeah, this is assuming Binyam's right, that if A exists, so this is assuming that if A exists. If the inverse A doesn't exist, you can't solve the system this way. But, anytime you take an identity matrix, like if you take 1, 0, 0, 1 and multiply it by 3, 4, you're going to get back 3, 4. But this is the reason, this is one reason for learning about inverses. Okay, one reason for learning about inverses. And they have an actual application where, let me just see here, one moment. Hold on. They talk about a deflection of an elastic beam in example 3, and that'll be useful for one of your homework problems. But I won't go into detail on that now. But let's just, are there any questions on this? All right, well, let me go ahead then. May I move off back to the book? Okay. All right, I'll wait. All right, are there any questions at all? Okay, it's all right, Matthew. All right, Binyam. All right, very good, Matthew. Okay, so the conditions you're going to learn about actually in section 2.3. It's a good question, Binyam. He's wondering about, well, how do we know when we have an inverse? You'll see that a little bit in 2.3. No, it's a good question. Good question. That's fine. Okay, so, all right, I'm going to go past the beam problem and go to example 4 here. So here, they say use the inverse of matrix A in example 2 to solve the system. So you have this system 3x1 plus 4x2 equals 3 and 5x1 plus 6x2 equals 7. So the A matrix is going to be what? What would the A matrix be here? If you think about A times X equals B, taking this system of equations and writing it as a matrix equation, what would A be? What would A be? A has to be a 2 by 2 matrix. That's right. 3, 4, 5, 6. 3, 4, 5, 6. So, and they found the inverse back in example 2 using the formula. They found the inverse, A inverse, to be equal to -3, 2, -5 halves, and -3 halves. Okay, that's what they found it to be. And so then X will equal A inverse times B. And that's yet another way to do it. Now, in practical work, there are numerical notes at the end of every section. So section 2.2, I'll show this numerical note, but inverses for big matrices are going to be very labor intensive to compute, and I'll show you why. But all right, so I want to say, what I'm trying to say is you're going to see an algorithm. You in the previous problem there, you computed A inverse using the formula for an inverse for a 2 by 2 matrix. But later on, you're going to see an algorithm for computing the inverse for a general n by n matrix. And for large matrices, it can be labor intensive to use the algorithm directly. Okay, and so in practical work, for large matrices, we don't normally compute the inverse directly, but nevertheless, the theory behind computing the inverse is going to be very important. And of course, we can get inverses by hand for small matrices, 2 by 2s, 3 by 3s, that sort of thing. Okay, so here we have a theorem, theorem 6. Theorem 6, let me just see here, gives some rules for inverses. So if you have the inverse of an inverse, that'll equal, if you have an inverse of a matrix and you inverse that, that's going to give you back the matrix. That makes sense. If you have the product, if you have the part B of theorem 6, if you have the product, the inverse of a product, that will equal the product of the inverses in reverse order. In reverse order. Okay. Now, that's not hard to show. Let me show you why that's true. They have here behind, after every theorem, they have a little proof. This theorem isn't hard to prove. If you take A times B and multiply it by B inverse A inverse, matrix multiplication is associative. So we can regroup the multiplication as, so I'm at this step right here. Let me get it with my highlighter there. So you can, matrix multiplication is associative, so you can regroup how you multiply. Group B and B inverse together, and then the A's to the left and the A inverse is to the right, but B times B inverse is the identity, and so you get A times the identity times A inverse, that equals the identity. Okay, similarly, you could show that B inverse times AB equals the identity. You have to prove it both ways, because sometimes you'll have a matrix that when you multiply, like a matrix A times a matrix B, you'll get the identity, but that doesn't mean the matrix A is the identity, because you also have to do then B times A to get the identity. You have to show it both directions. And then finally, for theorem 6, this C part is, if you have an invertible matrix and you have the transpose of it, the transpose of the inverse, or I should say the inverse of the transpose, is the transpose of the inverse. So this is theorem 6, and you don't need to copy the rules down. They're in your book. But are there any questions? Let's see, hold on. Wastina says, can you explain why the order matters in B? Wastina, the reason the order matters is because of the proof. The proof shows that you have to have B inverse times A inverse. A times B times B inverse A inverse will give you the identity. And B inverse A inverse times AB gives you the identity. So you know the inverse of A times B is B inverse A inverse. It's because of the proof there. Okay, does that make sense? A times B is, yes, A inverse B inverse is different from B inverse A inverse. Absolutely. 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 Okay, you're welcome. You're welcome. Are there any other questions before we move on here? That's right, Benjamin. Matrices are not commutative. That's right. All right, well then let's keep going here. Let's keep on moving here. The one thing too they mentioned is that if you have the product of invertible matrices, and if the product's invertible, then the inverse is the product of their inverses in reverse order. We just saw that with theorem 6. Let's move on here. Now, something that's mentioned here in this section 2.2 are something called elementary matrices. An elementary matrix is one that is obtained by performing a single elementary row operation on an identity matrix. The next example illustrates three kinds of elementary matrices. Okay, so like for the first elementary matrix, you notice E1, there's a -4. There's a -4 right here in the bottom left-hand corner. So how could you go from a 3x3 identity matrix? What operation would you have to do so that you would get a -4 in that spot there? What operation would you have to do? What row operation? So in other words, what I'm saying, let me go to the board here. Hold on. Okay, so here's the I sub 3. And E sub 1 is 1, 0, 0, 0, 1, 0, -4, 0, 1. So they did a row operation. They did a row operation on that I3. Ah, good. So if you take, very good, everybody. If you take -4 times the first row and add it to the third row, and replace the third row by that result, that gets you E1. That's what they mean. That's what they mean by an elementary matrix. That's all they mean. All right. Are there any questions? All right, well, let me go back to the book here. What about the second matrix here? What did they do to the identity to get the second matrix? E2, E sub 2. What row operation was done? That's right, Solon. They switched the first and second rows. That's an elementary row operation. Okay, what about the third one? What about E sub 3? What did they do there? Good, they multiplied the third row by 5. And again, another elementary row operation. Now, elementary row operations have some nice properties, which is why they talk about them a little bit here. Okay, I won't worry about the last matrix there. Okay. So one thing is every elementary matrix is invertible. Every elementary matrix is invertible. Okay. All right. So that's one of the key things. One of the key things they want to mention here. Now, you see, these elementary, the reason we need to understand these elementary matrices is because they're used to help us prove things in linear algebra. So remember, you have a theorem theorem, or you have a formula that allows you to compute the inverse of a 2 by 2 matrix. But we want a method that's going to help us find the inverse of any square matrix. Okay, and it says here in theorem 7 that a n by n matrix is invertible if and only if the matrix A is row equivalent to the identity matrix. And in this case, any sequence of elementary row operations that reduces A to the identity matrix also transforms the identity matrix into the inverse matrix. Okay, so this is going to help us understand the process for finding the algorithm for finding the inverse of a matrix. And actually, what I have is I have a nice example that I worked out here. And what I'd like to do is bring this example in to our lesson. So give me just a moment. I'm just gonna look at the book a little bit, and that's fine. But let me bring that up. One moment. Okay, so let me get it here. Just got to get it. Here we go. Thank you for your patience. So this example is like my little example to help you understand a little better about elementary matrices and how they can be used to promote this algorithm from theorem 7 from section 2.2. Okay, so take a moment. We'll start off simple with a 2 by 2 matrix. Take a moment to copy this down. Okay, so we're going to let A be the matrix 2, 3, 1, 4, and we want to show that the same sequence of elementary row operations that reduces the matrix A to the identity also reduces the identity to A inverse. You see, what the goal is we want to find A inverse. If we have a square matrix A, we want to find A inverse. But we need a general approach that will work for any size square matrix, 2 by 2, 3 by 3, 4 by 4, and so forth. All right, let me go to the next page. Everybody's good? Okay. All right. What I'm going to do on the next page is do the algorithm. I'm going to do the algorithm. Okay. Okay, great. Thank you, Matthew. So in the book, there's an algorithm for finding the inverse. The algorithm says row reduce. Well, I want to be a little bit careful here. I'm not actually ready for that yet. I'm not actually ready for that. Let me stick with this here. Okay. All right. So let me go now back into the example. Okay. All right. So look what I'm doing here. I'm going to do row reduction of the matrix A to its identity. It's like taking, I mean, you're used to taking systems, augmented matrices, and getting them in reduced echelon form. That's what we're doing here, but we don't have a system. We have a matrix A. But reduced echelon form is defined for any matrix A. Okay, so what I do is the first step, so 2, 3, 1, 4, that matrix, then I do a row operation. I switch the first and second rows, and that matrix becomes 1, 4, 2, 3. And then I want to get a 0 where the 2 is. So we'll multiply the first row by -2 and add it to the second row and replace the second row by that result. Then where the -5 is, we want a 1 there. So I'll multiply through the second row by -1/5. And then finally, we want a 1 where the 4 is. So I'm going to take -4 times the second row, add it to the first row, and replace the first row by that result. And that gets me to the identity matrix. So it took a series, let's see, 1, 2, 3, 4 row operations to get this matrix in reduced echelon form. Are there any questions up to here? All right. I want to give folks a chance to catch up. All right, so once again, the first row operation we did, we did, how many row operations did we need to convert A into reduced echelon form? How many again did we need? 4. That's right. That's right. Now, every one of those row operations that we did, for every one, there's a corresponding elementary matrix that if we multiply that matrix, the matrix A, on the left, we can simulate the row operation. So let me give you a chance to copy this down. These are our elementary matrices. E1 is first, E2 is second, E3 is third, and E4 is fourth. Okay, take a moment to copy those down. Okay, you're welcome, Moshe. Okay. So, all right. So first, what we want to consider is taking E1. Actually, I can do better than that. I got my little rectangle thing here. Well, hold on, maybe not. Just give me a moment here. Rectangle. Okay, when you multiply the first elementary matrix, E1, Matthew, I had to figure out what E1, E2, E3, and E4 were. But, you know, I mean, I know that, what was the first thing that we did in our, I want to say this the right way. Okay, when we did our row operations, what was the effect of the first step? We swapped rows, that's right. So if I multiply the matrix 2, 3, 1, 4, the matrix A, by the elementary matrix 0, 1, 1, 0, that's going to produce a row swap. It swaps the first and second rows. As you can see, we get here 1, 4, 2, 3. Okay, so far are we okay? You're going to get used to these, figuring out what elementary matrix will do what. But elementary matrices simulate row operations. Elementary matrices simulate row operations. So now, like, for example, the second row operation was what? How did we get the 1, 4, 0, negative 5? What did we do again? All right, that's right, Biniam. We took negative 2 times row 1 plus row 2. Okay, well, if we, maybe I'll put it in green here. Hold on. A lot of stuff to click and touch here. If we take the elementary matrix 1, 0, negative 2, 1 and multiply it by the 1, 4, 2, 3, that will get us 1, 4, 0, negative 5. And how did I come up with the elementary 2 matrix? Well, I took the identity matrix, multiplied the first row by negative 2, and added it to the second row, and replaced the second row by that result. That's how I came up with it. So, like, for instance, the E1 matrix, 0, 1, 1, 0, that's just the identity matrix where I switch the rows, swap the rows. That then, when I multiply A by E1, that swaps the rows of A. But now I have this 1, 4, 2, 3 matrix in this step here. And by taking the elementary matrix and taking negative 2 times the first row, adding it to the second row, and replacing the second row by that result, I get the elementary matrix that's going to then, by multiplying by E2, by the 1, 4, 2, 3, I get the matrix 1, 4, 0, negative 5. Now, how did we get 1, 4, 0, 1 on the third step? How did we get 1, 4, 0, 1? What did we have to do on the third step? We multiplied the second row by negative 1/5. So what am I going to do to get the elementary matrix? That will do that. I'm going to take the I'm going to take the identity matrix and do what? Multiply the second row by negative 1/5, and that's how you get E3. The identity matrix by, and that's how you get E3. Okay, and so then we get the 1, 4, 0, 1. Okay, hold on here. Let me just see here. And then finally, 1, negative 4, 0, 1 times 1, 4, 0, 1, that's going to give you the identity matrix. So the last elementary matrix was 1, negative 4, 0, 1. That came from taking the identity matrix, multiplying the second row by negative 4 of the identity matrix, adding it to the first row of the identity matrix, and then replacing the first row of the identity matrix by that result. Okay. So all we're doing here, is we're just, what I did here, Biniam's right. The elementary matrices allow you to visualize the row operations better. So all we're doing is we went through the process of doing 4 row operations to get to the identity matrix. Every row operation we did can be represented by an elementary matrix, meaning when we multiply the elementary matrix by the matrix A, it'll simulate a row operation. So the first row operation we did was we got 1, 4, 2, 3. If I take the elementary matrix 0, 1, 1, 0, that's a row swapping elementary matrix, and multiply it by 2, 3, 1, 4, that gets me 1, 4, 2, 3. Okay, the second row operation that we did to get 1, 4, 0, negative 5, the elementary matrix that'll do the job there is E2. Okay, and then you got the 2 remaining row operations. So this is something you're probably going to have to look at a little bit. If you don't, I mean, I'm just trying to give you sort of a feel for it. But basically, these elementary row operations, when you want to do something, when you want to do a row operation on a matrix, you could simulate that row operation by finding the appropriate elementary matrix and multiplying the matrix on the left by that elementary matrix. And we did it 4 times here. So now this is important. This is important because let me show you on the next page what this means. So what this means is that then E4 times E3 times E2 times E1 times A equals the identity. Okay? And all of these elementary matrices, all 4 of them, each one, every elementary matrix is invertible, meaning that the product of the elementary matrices is invertible. So that means that the inverse of E4, E3, E2, and E1 is defined. Let me let you copy up to this step here, okay? Yes, Matthew. All right. The purpose of this exercise, this example, is to help you understand the algorithm that you're going to see. Matthew asked the inverse of 4 elementary matrices times the 4 elementary matrices equals the identity. Oh, yes. Yes, it does. Because, I mean, E4 times E3 times E2 times E1 is a matrix. So the inverse of that matrix times the matrix is, yeah, equal to identity. Good question. So now what we have, of course, if we multiply by the inverse of E4, E3, E2, E1 on the left, like we're doing in this step here, we have to multiply on the left, on the right side of the matrix equation. So this means then that A, the matrix A, is equal to the inverse of E4, E3, E2, E1. But remember what we're interested in finding. We're interested in finding the inverse of A. Well, to find the inverse of A, right, all you do then is take the inverse of both sides of the equation, and you'll see then that the inverse, you'll see that the inverse then is just E4 times E3 times E2 times E1, or you can think of the inverse as E4 times E3 times E2 times E1 times the identity matrix. So what this means is, let me let you copy it and then I'll comment on it. So Solomon, what I want you to do, we can, when class is over, we can take a look at that part together. And I'm not saying you're the only one who might not be quite comfortable yet. I understand that. This is a kind of problem where we might have to look at it a little bit outside of class. But I'll tell you what, after class, I'll bring that second part up again, and we can go over it again together. How does that sound? And don't forget, it is on the recording. We are recording this, so that's a nice thing about recordings. You can play them back and play them back. How many have taken a recording and played them back and maybe a few times? Has anybody done that with any of the class recordings? Oh, you're welcome. All right, Christy has, Kevin, Vivian. Wow, okay. Getting a number of people. Good. All right, so remember that we took the matrix A and performed 4 row operations on it to get the matrix A into reduced echelon form. And that means the identity matrix. Any square matrix in reduced echelon form will be the identity matrix, of course. Okay. It turns out that if we do the same 4 row operations, and when I say the same 4 row operations, I represent that by, E4 times E3 times E2 times E1. I can do the same 4 row operations, multiply it by the identity matrix, and that'll get me the inverse. So therefore, the same sequence of elementary row operations that reduces the matrix A to the identity also reduces the identity matrix to A inverse. and this is the key for to finding the inverse, to finding A inverse. The same sequence of row operations that reduces the matrix A to the identity matrix will reduce the identity matrix to the inverse of A. And we did this for a simple 2 by 2 matrix, but it would hold for any size matrix. So what I want to do now is show you this algorithm, which corresponds to example 7 in the book, to show you how to find an inverse. All right. Are there any questions so far? All right. Well, let me stop sharing here. Everybody has it copied okay? We're good? All right. All right. Wonderful. All right. Well, let me get back to the book now. Let me see. Where is the book here? Hold on. Where is the book? One moment. Now I'm looking for the book. I mean, I have it, but I got to find it in my thing. I just had it. Why isn't it there? Hold on. What I'm trying to do is bring up the example 7. From the book here. All right, let me go out and come back in. I really don't want to go anywhere at all. But let me just get it here. Okay, good. Hold on. You have to forgive me if I... Okay, now let's see. I ought to be able to bring it up here. There it is. That's what I was looking for. Okay. So here's the algorithm to find the inverse. You create an augmented matrix where the matrix has, the matrix itself has the matrix A and the identity side by side. Okay, if A is row equivalent to the identity, then, well, they just have some words there. Let me show you here. So look what they do here. The matrix A here is 0, well, it's this 3 by 3 matrix. They put it here. I don't want to have it all show, but they put the matrix here. They create a 3 by 6 matrix, 3 rows, 6 columns. The first 3 columns are from the matrix A. What do the last 3 columns represent? First 3 columns is the matrix A. Last 3 columns is the Identity. Good. Good. So our goal is to get the matrix A into reduced echelon form. But the row operations that we use to get the matrix A in reduced echelon form simultaneously will also be used to get the identity matrix into the inverse. So the row operations that reduce the matrix A to the identity are the same row operations that will transform the identity matrix into the inverse matrix. So like for instance, they want here in the first column, they want zeros where the 1 and the 4 are. So they're going to take their, well, no, you gotta, hold on here. Hold on, what are they? Oh, okay, I'm sorry. I want to go over here. See, now they're not doing vertically. They're going left to right, left to right. So this is the next stage here. So what do they do? What do they do in actually the first step here? What did they do to get that matrix that I've highlighted in yellow? They switch rows 1 and 2. They do it for the matrix A and the identity. Then, in the next step, what did they do? What did they do to get to the next step? They went -4, good, so I'm at -4 times row 1 plus row 3, and put that result in row 3. Because they don't want the 4, they want the 4 in the bottom left-hand corner to be a 0. They're trying to get the matrix A in reduced echelon form. Okay, now you want a 0 where the -3 is. So they do a row operation to do that. But they do the same row operation on the identity. Okay. And then they do 2 more row operations, two more row operations, until finally they row reduce the matrix A as they reduce the matrix A to the identity, but then this matrix on the right to the identity, the -9/2, 7, -3/2, -2, 4, -1, 3/2, -2.5, that matrix is automatically your inverse. That matrix is automatically your inverse. And the reason this works is because the row operations that will reduce the matrix A to the identity matrix are the same row operations that will transform the identity matrix to the inverse. That's why they put the identity next to the matrix A in the beginning. How many think that's absolutely cool? Yeah, it makes sense, Robin. It takes a little time to think, but how many think that's kind of cool? Yeah, very cool. And actually, you know, when I started teaching back in the 90s, this is how they found, I taught courses, thank you. Well, actually, when I took linear algebra in college at the University of Maryland, this is how, like on exams, we found the inverses. We didn't have any, you know, computer software to help us. And I remember on one exam, I had to find the inverse of a 4x4 matrix by hand. And that's how we had to do it. We didn't have calculators and things to help us. But in your homework for section 2.3, you're going to have some problems where they want you to use the algorithm to find the inverse. So they want you to go through the steps. Yeah, Christy, it was rough. It was rough. So that's right, Matthew. If you have a 4x4 matrix, you make it into you use a 4x8 augmented matrix. That's right. Where the first 4 columns are the matrix A, the last 4 columns are the identity. Okay, so that's that's you know, what I wanted to show you. And they talk about, they have these numerical notes at the end of the section where in practical work, they say that A inverse is seldom computed unless the entries of A inverse are needed. Computing A inverse and A inverse times the vector B takes about 3 times as many arithmetic operations as solving AX equals B by row reduction. And so row reduction may be more accurate. Like, for instance, if you're, you know, just, you know, round off error, that sort of thing from a computer. But nevertheless, there are ways to get the inverse very nicely if we do so, if we factor the matrix A as a certain kind of product, like an LU factorization. Then the inverse is easier to find. But we'll talk about that in our next class. All right, so if there's no questions on this, let me stop the recording. I want to talk